In this quick video, we are going to look at exponential functions. Just a quick concept review, that's it. It's not going to be too detailed. It's going to be just a quick conceptual understanding. So, you know that any exponential function is of this form, where c is some constant, a real number. This b is the base. The restriction on the base is that it has to be greater than 0. It cannot be negative, and it cannot be 1 either. Okay, so that's it. And the domain of all exponential functions is all real numbers. So there are three key points. So let me just look at a function, say 2 to the power of x. So the three key points that I use to graph this function are, the first key point is this -1 followed by 1/2, because so you can create a small table if you want for all the exponential function graphs. So the three x values I'm using are these three. So 2 to the power of -1 is 1 over 2 to the power of 1, which is 1/2. Okay, so a negative exponent does not mean a negative output. It just means it's a fractional output. It is small, right? So then 2 to the power of 0 is 1. 2 to the power of 1 is 2. So this is the second point, and this is the third point. Okay. Some of the features of this graph are that the domain is all real numbers. The range is 0 to infinity. The y-intercept is 0, 1. There is no x-intercept, and the horizontal asymptote it at y equals 0. Now, any vertical shift to this graph changes the range as well as the horizontal asymptote. So, for example, if I want to graph another function and I call it 2 to the power of x minus 3, then what happens is every y value moves down. So basically, this y equals 0 horizontal asymptote is now first moved to y equals -3. The first point that I had here, this point, is going to now move to -1, -2.5, because I subtracted 3 from half. This is going to become 0, -2. This is going to become 1, -1. So my graph is going to look like this. So as you can see, the domain doesn't change for this graph, but the range sure did. So the range became from -3 to infinity now instead of 0 to infinity. And this comes from the vertical shift downwards, right? What else changed? The horizontal asymptote changed to y equals -3. Nothing else changed. Of course, yeah, there is an x and y intercept now. Previously, there was no x intercept. Now you have one. The y intercept became -2 instead of +1. So the y intercept also got subtracted by 3. You will notice that any kind of horizontal shift will not change your anything. So if of course it will change the y-intercept, but not the range or the domain or the horizontal asymptote. Okay, so for example, if I want you to graph what is, let's say, h of x is 2 to the power of x plus 1, right? So then what do I do? Every x value moves to the left by 1 unit. Remember, left by 1 unit. So this one will now become -2 1/2. This will become -1 1. And this will become 0 2. So your graph is going to be like this now, right? So this is the graph of 2 to the power of x plus 1. This was the graph of 2 to the power of x minus 3. This was the graph of 2 to the power of x. So what happened? The graph got shifted to the left by 1 unit. Did the domain change? No. Did the range change? No. Did the horizontal asymptote change? No. Did the y-intercept change? Yes, it did, right? Your graph still does not have a x-intercept. Okay, so what can change my range, right? So let us look at this. So suppose, say, I have this graph, right? The graph that I have been working on right now, which is 2 to the power of x. Let's say I want to graph, this is 2 to the power of x. So let's say I'm graphing 2 to the power of x plus 1 minus 3, like putting it all together, what I did just now, right? So my original 3 key points were these. So now my x value is going to be moved by 1. So these are the original 3 key points. My new 3 key points are going to be x becomes -2, -1, and 0. Y becomes -2.5, -2, -1. So what are my new points? My new points are -2, -2.5, somewhere here, -1, -2, somewhere here, and then 0, -1 is here. My asymptote is here. Okay, so my graph is like this. Sorry about this graph, like that. Okay, so if you look at it, the domain did not change for this one, right? So I'm going to keep consistent with the colors here so that we are not confused. So if you look at this domain, it's the same. The range, of course, changed from -3 to infinity, and the horizontal asymptote changed to y equals -3. Now, suppose, say, I ask you to graph, the only change I'm making is I'm making this negative. Okay, so this is a reflection, right? Reflection about the x-axis. So your 2 to the power of x plus 1 graph, right? 2 to the power of x plus 1 graph slightly moved to the left, and then it got flipped, and then it got moved further down, right? So now what happens is, if I'm coming up with the 3 key points, this is how they will look like. So my 3 key points are going to look like this. So what am I going to do? First, I'm going to do the x values, and then we'll do the y values, okay? So I'm writing the original 3 key points first. These are the ones in the white are the original 3 points. Then we will write our new points. In the new points, what will happen is the only change that happens to the horizontal transformation is moving to the left. So that is the only change. Whereas what is happening to the y values? It's first becoming opposite and then subtracted by 3. So opposite of half is -half. And then I further take away 3 from it. Opposite of 1 is -1. Further take away 3 from it. Opposite of 2 is -2. Further take away 3 from it. So where are my points now? The points are -2, 3.5. It comes down. Then -1, -4 is even further down. 0, -5 is even down. So my graph is actually flipped like this. Sorry about the graphs. So it's like this, right? So this is the graph of -2 to the power of x plus 1 minus 3. The other one was the graph of 2 to the power of x plus 1 minus 3. There was no negative. Now, once the graph is flipped upside down, you can very well see that the range is now changed, right? So the range of the green graph now is -infinity to -3, just became opposite, right? And the horizontal asymptote did not change, however, it is still at -3 because the horizontal asymptote only comes from the vertical shift. That's it. Okay. So that is the graph of an exponential function. So now let us move on to what do we do next here? Let's solve a few equations, perhaps. So what if the value of the base is between 0 and 1, right? So for example, when the base is 1/2, 1/3, and so on, your graph is now going to be a decay function, like so. So this will be the graph of 1/2 to the power of x, whereas my graph of 2 to the power of x was like this. So in 1/2, so this is called an exponential growth function, the 2 to the power of x, whereas this is an exponential decay. As you can see, 1/2 to the power of x is constantly decreasing, whereas 2 to the power of x was constantly increasing. Both of them have the same domain, same range, same y-intercept, but one is a growth, one is a decay. Okay, and one more function that I want to talk to you about is the natural exponential function, which is written as e to the power of x. So e to the power of x, e has a value. It is an irrational number. Its value is something like 2.718, goes on and on and on. So it is non-repeating, non-terminating decimal. It is an irrational number. So since it is between 2 and 3, you're going to have a graph that is also going to be like slightly more like this. So this is the graph of e to the power of x. Okay. So what is e to the power of x? It is just e is an irrational number. Okay. Just like pi, it has a value of 2.71828 and then it goes on and on. So that is what it is. There will be a separate video on just about E, right? But right now, for the purposes of graphing and the purposes of just getting an idea of exponential function graphs and solving simple equations, those are the two concepts covered in this video. This is enough, right? This is all we're going to talk about E now. So now let us look at solving some simple equations. So I have just put some basic 4 equations here that we will solve. In the first equation, I have 5 to the power of x minus 1 as 125. I can rewrite my right-hand side as a base 5 exponent. 5 times 5 is 25 times 5 is 125. So 125 can be written as 5 to the power of 3. Once I have my left-hand side and right-hand side written as exponents with the same base, then the only way this statement can be true is if x minus 1 is 3. Then solve x is 4 is the solution to this equation. In the second problem, the base is already the same for the exponents on both sides, which means I can set the powers to equal one another. Then a little bit of rearrangement gives me this, and my x is 6/5. In the third problem, 27 and 9, it's hard to write 27 as a base 9 exponent, 9 as a base 27 exponent. However, they can both be written as a base 3 exponent. So 27 is 3 to the power of 3, the whole thing raised to the power of 2x. This is 3 squared raised to the power of x plus 2. The law of exponents says that when you raise a power to another power, multiply them. So 3 times 2x is 6x. This becomes 3 to the power of 2 times x plus 2. Remember to use parentheses, please. Now we have got the two exponents with same base. So now I can set up an equation that looks like this. I distribute the right-hand side. I move the 2x over here. X equals 1 is my answer. Okay. Last one. Again, I use the law of exponents. The left-hand side can be combined like this. The right-hand side is this. Both the left and the right are the same base exponents. So I set up an equation like so. Bring all the terms to the left. Factor. I have two solutions. X can be -3 or 1.